Welcome to episode 85 of your CySA Plus Prepcast. Today's episode is focused on insecure design patterns, a foundational and often underestimated source of security vulnerabilities that originate not in code, but in system and software architecture itself. These architectural choices or systemic omissions create the environment in which security issues flourish, even before a single line of code is written. As we examine how these flawed designs emerge, how they differ from implementation bugs, and how they are identified and mitigated, we'll establish a framework that will help you tackle exam questions and real-world security analysis with greater insight and clarity. This episode is critical to your exam readiness and directly contributes to your success as a cybersecurity analyst. We begin by defining insecure design patterns as recurring flaws in the way applications or systems are architected. Unlike basic coding errors or configuration oversights, insecure designs are embedded early into the software development lifecycle, often stemming from incomplete threat modeling or poor architectural choices. These patterns result in security vulnerabilities that cannot be fully resolved with patches alone, and often require a full design reconsideration. Understanding this distinction is key for analysts preparing for the exam and seeking to implement lasting cybersecurity solutions. Cybersecurity analysts distinguish insecure design patterns from mere programming mistakes because they exist at the design level rather than the implementation level. A design pattern may appear functional from a development standpoint, yet still harbors systemic weaknesses that invite security compromise. For example, if an application's design assumes users are always trustworthy without enforcing authorization checks, the resulting system is flawed regardless of how securely the code is written. Recognizing this separation between design flaws and code-level issues enables analysts to think strategically and holistically. Among the most common insecure design patterns is the use of weak or insufficient authentication mechanisms. When systems rely solely on user-supplied passwords with no additional safeguards, or when multi-factor authentication is poorly implemented, attackers have a direct path to bypass security protections. Insecure session management can amplify these weaknesses, making it easier for threat actors to maintain unauthorized access once credentials are compromised. Authentication should be viewed as an architectural requirement, not just a coding task. A closely related design issue is the absence of robust authorization controls. In some systems, users may authenticate successfully, but are not properly restricted in what they can do afterward. Poorly defined access control models allow privilege escalation and data leakage. When authorizations treated as an afterthought, rather than an integrated part of system architecture, it leaves the application open to abuses that are not easily addressed through conventional patching or policy updates. Analysts need to identify these issues during the planning and design stages to ensure long-term protection. Another dangerous design pattern is insecure communication. When system designers fail to incorporate secure transport mechanisms, such as strong encryption protocols for data in transit, sensitive information becomes exposed to interception, manipulation, or replay attacks. Insecure communication designs might also neglect proper certificate validation, ignore the use of HTTPS, or allow mixed-in common scenarios. Each of these creates vulnerabilities that stem directly from flawed architecture, not user behavior or misconfigured devices. Insecure error handling represents another major design flaw often observed in systems that reveal too much information when something goes wrong. For example, verbose error messages that display database queries, server stack traces, or internal file paths can unintentionally equip attackers with valuable reconnaissance data. These disclosures often result from inadequate planning for secure failure modes, and correcting them typically involves redesigning the system's interaction with end users and internal logging systems. Analysts must also remain aware of insecure data storage designs which result in sensitive information, such as passwords, API tokens, and personal identifiers, being stored in plain text or using outdated encryption algorithms. Systems that fail to segregate critical data or lack access controls at the storage level create long-term risk that are not always visible during routine scans. Such storage decisions must be made early in the design process with a clear understanding of threat models and compliance requirements. Equally important is the absence of strong input validation mechanisms throughout a system. If a system design allows unfiltered user input to flow into back-end systems, such as databases or file storage, then injection attacks become not just possible, but likely. Without a clearly defined validation layer built into the architecture, no amount of coding discipline can prevent attackers from manipulating system behavior through crafted inputs. Poor session management also constitutes a widespread insecure design issue. Analysts observe situations where session tokens are not properly randomized, where sessions are not invalidated after logout, or where cookies are not protected with attributes such as secure and HP only. These oversights result from design decisions, not development errors, and often expose users to session hijacking, fixation attacks, or unauthorized impersonation attempts. Detecting these issues requires architectural insight as much as penetration testing. When analysts identify insecure design patterns, they must go beyond documentation to assess risk implications and propose secure alternatives. This process typically includes outlining how the design enables exploitation, what data or systems are at risk, and how redesigning the component or process would eliminate the underlying weakness. Remediation efforts must be accompanied by updated documentation, threat models, and validation procedures to ensure ongoing accountability and improvement. For more cyber-related content and books, please check out cyberauthor.me. Also, there are more security courses on cybersecurity and more at baremetalcyber.com. Cybersecurity analysts often begin their secure design assessments with threat modeling and design reviews that occur early in the software development lifecycle. By evaluating architecture diagrams, data flows, and system boundaries before development begins, analysts can detect architectural weaknesses before they materialize into actual vulnerability. This proactive step is essential because once insecure patterns are embedded into production systems, remediation becomes more complex and costly. Among the many threat modeling approaches, the STRIDE framework is a commonly used technique for systematically identifying potential insecure design patterns. STRIDE stands for spoofing, tampering, repudiation, information disclosure, denial of service, and elevation of privilege. Each category represents a type of threat that maps directly to potential flaws in system architecture. For example, spoofing can highlight flaws in authentication design, while information disclosure points to weaknesses in data transmission and storage architecture. In addition to manual threat modeling, analysts utilize automated static analysis tools to identify insecure design patterns embedded in codebases or architectural components. These tools can analyze configuration files, access control logic, and system workflows to detect indicators of flawed design. Tools integrated into development environments or CI/CD pipelines help enforce secure architecture principles consistently across all phases of development. Despite the effectiveness of automated scanning, analysts often complement these tools with hands-on assessments such as penetration testing and manual code review. This combination allows them to validate whether detected issues are exploitable in practice and whether they stem from deeper architectural weaknesses. Manual testing is particularly useful in identifying complex interaction flaws, such as session fixation or multi-stage privilege escalation, that automation alone may not detect. To prevent insecure design patterns, analysts champion secure design principles from the earliest conceptual phases of development. These principles include adopting secure defaults, enforcing the principle of least privilege, designing layered defenses, validating inputs at every trust boundary, and selecting proven authentication and session control methods. Promoting these principles requires organizational alignment between security teams and development leaders. Effective collaboration is critical. Analysts work closely with software architects, project managers, and QA teams to ensure security is embedded into every design decision. This collaboration spans architectural reviews, code walkthroughs, functional testing, and documentation updates. Embedding security into project management frameworks ensures it is not sidelined as a post-development concern, but is treated as a core requirement from day one. When insecure design patterns are found in existing systems, remediation often involves redesigning system components rather than merely applying patches. Analysts may recommend the adoption of standardized security frameworks or architecture templates that eliminate design ambiguity. Secure design patterns, such as those published by OWASP, offer tested blueprints for implementing secure authentication, input handling, and data access controls. To sustain secure design practices, analysts encourage ongoing training for all project stakeholders, including developers, testers, architects, and managers. These training programs emphasize real-world consequences of insecure architecture and equip teams with the skills needed to evaluate and implement secure design principles. Without continuous learning, teams may inadvertently revert to insecure practices due to lack of awareness or familiarity with current threats. Monitoring plays a key role in identifying the exploitation of insecure design patterns that may still exist in legacy systems. Real-time analytics, intrusion detection systems, and anomaly detection platforms help analysts observe suspicious behaviors that may indicate design-driven weaknesses. For instance, repeated session hijacking attempts may reveal insecure token handling, even in otherwise updated systems. Finally, analysts embrace continuous improvement in their secure design efforts. This involves conducting routine architecture reviews, updating threat models, refreshing training content, and auditing the effectiveness of previous design decisions. By creating feedback loops between detection, mitigation, and design, analysts can maintain an adaptive and resilient security posture, capable of addressing evolving threats. In closing, Episode 85 has explored the vital role of secure design in modern cybersecurity practice. Insecure design patterns are foundational weaknesses that, if left unaddressed, undermine even the most well-implemented security controls. Through proactive threat modeling, collaborative planning, design reviews, and continuous education, analysts can detect, remediate, and ultimately prevent these flaws. This approach not only supports your CySA Plus certification journey, but also equips you to influence the broader culture of secure development in your organization. As we continue through this series, keep these principles in mind and apply them consistently for long-term cybersecurity success. Thanks for listening. To learn more about cybersecurity, please visit baremetalcyber.com. There you will find best-selling books, videos, and even more free cybersecurity training courses. Please subscribe to the Prepcast and our various podcasts. And thanks for listening.